In this problem, we want to propose a mechanism that's consistent with two observations for the catalytic decomposition of nitrous oxide. One is that the rate's first order in N2O and zero order in oxygen. The other, it's first order in N2O and negative order in oxygen. So, not obvious when we start, but if we try different things, one that will be consistent is for have N2O, which is a gas, adsorb on a surface site, so this is not sulfur but a site on the surface, to form N2O on the surface. This N2O on the surface then decomposes to form nitrogen and an oxygen atom. Two of these oxygen atoms recombine to make gas phase O2 and free up two sites. So let's assume that the rate is proportional to the rate of the second step. In other words, the rate of reaction would be K second step times the coverage of N2O adsorbed on the surface. And then we're going to use a Langmuir isotherm for the coverage. I won't derive that. That's certainly done in a number of places. So we have an absorption equilibrium constant times the pressure of N2O, and then the same absorption equilibrium constant. But we also allow for the fact that oxygen coverage could be significant. And because it's oxygen dissociating, if we look at the isotherm for dissociative absorption, this is going to be raised to the 1/2 power. So that means the rate then is just the product of these two. So now let's look at this rate expression and try and see if it's consistent with the experimental observations. So look at the case where, for this mechanism, suppose we're at high temperature. And of course, we go to high temperature, these absorption equilibrium constants become small because the amount adsorbed decreases. Absorption is exothermic process, so as you raise the temperature, the absorption decreases. So that means under those conditions of high temperature, these terms would be small. And if that's true, then the rate at high temperatures would just be proportional to the pressure of N2O, consistent with that experimental observation. Well, the other extreme, let me give some room here, the other extreme is low temperature. And now let's make some assumptions that O2 is strongly adsorbed. Meaning the bond between the oxygen atom and the surface is a strong bond relative to this. So now we're going to say that this term dominates in the denominator and is large relative to the other two terms. And if that's the case, then the rate will be same numerator, but denominator, and this is consistent with the observation that the rate's first order in N2O and negative half order in oxygen. Now, this mechanism does not mean that it's because it fits these experimental observations, it doesn't necessarily correspond to the correct mechanism, but at least it's consistent with the observations.